Hey, this is it. This is it, you guys. Your final lecture for college prep chemistry. All right. So many of you, this is goodbye. Right. Some of you I will end up seeing in AP Environmental Science someday. Right. In which case you're going to get a lot more of these video lectures. But anyways, we are going to wrap up our final unit, and we are going to talk about Le Chateliers Principle. I think he's Australian. No, just kidding. Clearly Japanese. No, just kidding. All right. Clearly French. All right. So Le Chatelier, French chemist, and essentially what Le Chateliers Principle does is it allows us to make predictions about how equilibrium position shifts to decrease the stress that is added to a chemical system. Okay. And so when we talk about this stress, quote unquote, I'm doing finger quotes right now. You just can't see me. We're talking about predicting how a reaction will respond when we mess with the concentration, right? So if I adjust the concentration of my reactants or products from the outside while a reaction is going on, what's going to happen as a result, right? And we're going to do a qualitative prediction there. We're essentially predicting, are we going to make more products or more reactants when I do that? Okay. We're going to learn to predict qualitatively what happens when I mess with the temperature, all right? And that's going to involve understanding a little bit about the difference between an endothermic and exothermic process, which I will describe briefly in just a moment, all right? And then we will also learn how reactions with gases respond when we increase or decrease the pressure of that system. All right. So that's where we're going with this. And I'm going to put very little text on the screen over the next two slides. It's going to be lots of my wicked awesome drawings. All right. I'm hanging out with a guy from Boston. And so I'm starting to say wicked awesome and wicked cool and wicked smart, stuff like that. Anyway, you guys don't care about that. Let's move forward. So Le Chatelier and concentration. So, whoops. Guess what? Remember back in lecture 1, I said I want you guys to draw this bucket analogy for me, right? Because it's going to help us understand the Chateliers Principle. Well, here we are with the Chateliers Principle, and we're going to talk about how the concentration of our reactants if you adjust the concentrations, how's that going to affect our equilibrium position? And remember, we're describing equilibrium position as being to the right when we are forming products, and equilibrium position to the left when we're favoring the formation of reactants, all right? And there's a spectrum there, and we can shift it left or right based on changing conditions, okay? So let's go to our bucket analogy. So again, we're going to have two buckets, all right? And we're going to have those buckets connected, right, with an opening. All right, equilibrium is established in these buckets when the water level is equal in both buckets, right? And so again, in this case, our equilibrium position would be to the right because there is a larger concentration of products than there is in the reactant side, right? So our equilibrium position is to the right. And so what we want to be able to do, though, is predict what's going to happen if I change the concentration on my reactant side or my product side, right? So let's say our system's at equilibrium right now, right? We've made as much product as we're going to get, everything settled in. Now, what if I decided to come in and remove some of my product? So let's say I took some product out of the bucket. What's going to happen in this case? So if I were to remove some product, what would happen? What would happen is some of the reactant would shift into the product side. So removing the product will shift equilibrium position right. And that means we're going to make more. All right. And so the bucket analogy kind of helps us understand what would happen if I were to take some liquid out of my product bucket. Liquid from the reactant bucket would then shift into that product side. So removing product according to the Chateliers Principle, will shift our equilibrium position further to the right so that we make more product to replace what was lost. So the quote-unquote stress, again, doing finger quotes here, of the system was caused by removing product from the system as it's forming. So it's messing with that equilibrium. Okay? And likewise, what would happen if I added some product? So let's say I put some extra product into the system, right, as it's forming. What's going to happen? It's going to shift us back that way, right? It's going to send liquid back into the reactant side so that we achieve equilibrium again, right? And so if removing product shifts us to the right, adding product will shift us back to the left, all right? And we'll make more reactants. Okay, so that is essentially what happens. Now, likewise, we're going to apply this same logic, okay, if I messed with this side of the equation, right? If I removed reactant, right, that would shift us left. If I added reactant, it would shift us right. Okay, so according to the Chateliers Principle, and laboratory, of course, would justify this and support this thesis or this theory that removing product creates more product, okay? Adding product creates more reactant. Likewise, adding reactant creates more product. Removing reactant creates more reactant. All right? And so again, all I want you to do to help you picture what happens here is just use the bucket analogy. And the amount of liquid in each bucket refers to the relative concentration. All right. And if you took some stuff out of the product side, which way would it flow? If you added stuff to the product side, which way would it flow? And that tells you qualitatively how we're going to shift our equilibrium position. Okay. It is that simple. All right. You guys get some practice with this on ChemQuest, of course. Now let's talk endothermic and exothermic. All right. This is something I did not get much of a chance this year to try to drive home. We ran short on one of our units, and I didn't get to talk about it as much as I wanted to. But we're going to talk about it now. It's a fairly simple process, but endothermic and exothermic is referring to what happens during a reaction in terms of heat. Is the reaction endothermic, by which it absorbs heat from the surroundings, or is it exothermic, by which it releases heat to the surroundings? So, for example, let's say I got me some methane if I was from England, and I react that with some oxygen. Okay? Now, let's say I have a combustion, right? So in this case, methane and oxygen is going to produce, you guys know this, CO2 and water. Okay? But as you all know, when you burn natural gas, we also get a bunch of heat. Whoops, sorry about that. So if I combust, right? So yeah, we do need a little spark in there, okay? But it's not necessarily an addition to the system. It's just to get kick to start that. So if I combust methane and oxygen, I'm going to produce carbon dioxide, produce water, but I'm also going to produce a lot of heat. All right? So when heat is produced in a reaction, right, or released, we say that is an exothermic process. So when heat is written on this side, on the product side, we know then that it is an exothermic process. Okay? And so in another example, let's say I wanted to, decompose some water, for example. Okay, actually, no, that's not a good example. Let's say I want to decompose some sodium bicarbonate. All right, and in doing so, I'm going to produce sodium carbonate and some water and some CO2 or something. All right. When I do that, right? So in order to make that happen, I am going to have to add, right? So we've not been writing heat in our reactions. In order to decompose my sodium carbonate, into sodium bicarbonate, into sodium carbonate, water, and CO2, I am going to have to heat it up pretty hot. All right. And so in this sense, my reaction is not releasing heat to the surroundings. In order to make the reaction happen, I have to put heat into that system. All right. So when I just wrote H2O there because I'm a dingling, I meant to write heat. Okay. So it is an endothermic process when the process actually requires me to add heat to the system. All right. So exothermic, the heat is written on the product side. Right, and that is exothermic. Endothermic, the heat is written on the reactant side. And they're not necessarily a product or a reactant because they're not part of the original material. So it's just essentially, does the process release energy or does the process require energy? And so all of our energy producers, right, so burning natural gas or coal or the gasoline in your car, those are all exothermic processes because we get energy out of the system, and that's important when we're trying to generate energy, right? So all the things that require energy are endothermic processes. So like if you want to go home and fry an egg, for example, right, you actually are causing a chemical reaction in that egg. You're going to have to put heat into that egg, right? So that's an endothermic process. So you'd have egg plus heat yields yummy goodness. Right? So that'd be an endothermic process, right? Because the heat is on the reactant side. So with regard to the Chateliers Principle and heat, right, we're going to use the same bucket logic, right? So let's say again, I have CO2, methane, CH4, and O2, right? And just a little spark to get that process going. I produce CO2, I produce some water vapor, and a bunch of heat. All right, that's that energy we'll want to make use of. So in that process, okay, so what if I mess with the temperature? Okay, what if I add, what if I am combusting this and I increase the temperature of that system? All right. So again, we're going to look at this the same way we do with our concentration, right? So the heat is on our product side. So draw my little magic bucket over here. We're going to pretend heat's like a measurable quantity. What is a measurable quantity? But we're going to pretend it's a physical quantity, right, that we can measure, right? And so if my heat's on, if the heat is on my product side, that would be the same as, so here's my water level, right? That would be the same as adding something to my product side. So if I increase the temperature, right, that's going to decrease the ability of methane and oxygen to release that heat. All right? And so in reality, if I took and trapped all the heat that was being released so the temperature of the system increased, I would essentially slow down or halt the production of CO2, water, and heat, and I would push my equilibrium position back to producing more methane and oxygen. Now, I'd have to heat it up a lot for that to happen, but that's what would happen. Okay? So heat, we're going to treat just like the concentration. If the heat's on the right, we're going to treat it as part of the contents of the bucket on the right. And so if I were to cool this system off, right, I would then push the system back this way because that would be like removing stuff from that bucket. So if I took stuff out of this bucket, we're going to shift our position back that way, right? We're going to move to the right. So heat, we treat just like the concentration. If I increase products, right, or increase the heat of an exothermic reaction, so whatever side the heat's written on, right, remember makes it exo or endo. If I increase heat, if heat's one of my products, I'm going to push it back to the reactant side. If I decrease the heat and heat's a product, and so on. All right. So for concentration and for heat and endothermic versus exothermic reactions, you're going to have to remember that we treat it just like the concentration. We're going to use the bucket analogy again. All right. What you also have to remember is if it's an endothermic process, the heat goes on the left side. If it's an exothermic process, the heat goes on the right side. All right. And we could talk about that more when I get back, or you'll get some exposure to that in the ChemQuest as well. Moving forward. Pressure. All right. So let's say I got me some PCl5, phosphorus pentachloride, and I decompose that phosphorus pentachloride into phosphorus trichloride and chlorine gas. Now, we're balanced already. All right, so what I want you to pay attention to here is the fact that my reactant side has 1 mole. My product side has 1 mole of this and 1 mole of that for a total of 2 moles. Okay, now we have learned on occasion in this class that 1 mole of gas at STP will occupy 22.4 liters of space, right? So this 1 mole right here of gas would have a volume of 22.4 liters if it was 1 mole at standard temperature and pressure, right? Now, look at this side of my equation. I have 2 moles of gas. So the combined volume of these 2 gases when they decompose would actually be 44.8 liters, or twice as large. Okay, so that means, right, that in the decomposition of phosphorus pentachloride, right, I am going to have to either double my volume, right, or if it's in an enclosed container. So let's say I've got my PCl5 in an enclosed container, right, and so I cannot increase the volume. Well, there's a little relationship between gases, volume, temperature, so on, so on, so on, so on. But if I try to double volume or double my moles, I'm going to double the pressure. All right, so if this reaction is occurring inside this closed container, right, those gases are going to be pushing on the walls of that container. Right? You can see that happen in a balloon. When you blow in a balloon, the balloon expands, right? So the more volume you try to put in that balloon, the bigger the balloon has to get, right? Now, if you try to blow into like a propane tank, for example, that propane tank will not expand, right? So what happens is you push more gas into a propane tank, you just increase the pressure of that propane tank, okay? And so with the Chateliers principle, right, what it dictates is we're going to try to relieve the stress, or in this case, we're going to try to move our equilibrium position to the side that's going to decrease pressure. Okay, so again, so our equilibrium position, I'm going to write it as EP, adjusts to decrease the pressure. Okay, so let's say in this reaction, I decrease pressure. Whoops. All right, so I decrease the pressure in this system. So which way am I going to adjust? So we've already said that if I increase the pressure of a system, we're going to try to get away from that stress. All right, so let me just reword this for you. If I increase pressure, for example, rather than decrease, let's say I increase the pressure in this system. So it's already at equilibrium in the container that's in. So maybe I heat it up and that causes an increase in pressure. Which direction would the reaction go to relieve that stress? Right? It's going to try to decrease the amount of pressure, and the way to do that is to go to that reactant side, the side of the reaction that has fewer moles of gas, right? Because fewer moles of gas is going to occupy less volume. That will decrease the pressure of that system. So if I put higher pressure in this reaction, I'm going to move to the side that has fewer moles of gas to relieve that stress. And likewise, if we decrease the pressure, right, we would adjust our position back to produce more moles of gas because there wouldn't be a tendency to have less. Okay? And so with the Chateliers principle and pressure, we always move to relieve the stress of pressure, which means we move to the side that has fewer moles of gas, right? So now, sometimes you start with more moles of gas and end with less, and so it's not always going to move reactant or product side, right? It's just going to move to the side that has fewer moles. So we can't use our bucket analogy for pressure, which is why I didn't draw my magic buckets. All right. That concludes it. Your final lecture for the year is just over 20 minutes. Love you guys, and I'll see you in a few days.